Okay, in this video we are going to begin section 4.3, increasing and decreasing functions, and the first derivative test. In this section we're going to determine intervals on which a function is increasing or decreasing and apply this first derivative test to find the relative extrema of a function. And just a big overview of what we're going to do here. Say we have a function that has a few ups and downs in it. What we're going to do is take the first derivative and set that derivative equal to 0. That's going to show us our peaks and valleys, our critical numbers, the x values above and below where we're going to have horizontal tangent lines. So here in this quick function that I've drawn, there's a few peaks and valleys over the interval we're looking at. If we take the first derivative, set it equal to 0, we get these critical numbers where we're having our changes in direction, our peaks and our valleys. And what that did to the x-axis is chop it up into intervals. Let's look at starting right here. From this x value to this x value, we see the function is increasing. So we know from this over this interval our function is increasing. From the next critical number to the third x value here, we see our function is going down. So we have an interval where our function is decreasing. And then from this x sub 3 to x sub 4, our next critical number, we see the function is going back up, so it's increasing. That's just a broad overview of what we're going to do here in section 4.3. So increasing and decreasing functions. In this section, you'll learn how derivatives can be used to classify relative extrema as either a minima or a relative maxima. First, it's important to define increasing and decreasing functions. And of course, in math, we need everything defined very explicitly. So a function f is increasing on an interval if for any two numbers, x sub 1 and x sub 2, in the interval, x sub 1 less than x sub 2 implies that f of x sub 1 is less than f of x sub 2. And a decreasing function across an interval, if for any two numbers, x sub 1 and x sub 2, in the interval, if x sub 1 is less than x sub 2, that implies that the f of x sub 1 is greater than f of x sub 2. So more simply put, a function is increasing if as x moves to the right, as we're going to the right across the x-axis, the graph moves up. And it's decreasing if the graph goes down. And here's our theorem to test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b if f prime of x is greater than 0, or more simply, if the derivative is positive. If the derivative is positive for all the x's in some interval, then the function is increasing across that interval. And then similarly, if the derivative is less than 0, if we have a negative derivative for all x values across some interval, then our function is decreasing across that interval. And then we might run into a case where the derivative is exactly equal to 0 for a bunch of x's in some interval, then that means that the function is constant. It's going to have a flat spot. Increasing, our function is going up. We might have a spot where we're constant, where it's flat, and then we might have another part where we have a decreasing function. So here in example 1, we want to find the intervals on which f, this function, is increasing or decreasing. So first we have our function here is f of x is x to the third minus 3/2 x squared. So the first thing we want to do is find the critical numbers. Those critical numbers will chop our x-axis up into intervals. So let's find f prime of x. So here we'll have a 3x squared. And then here we'll bring our 2 down and multiply. We'll have 6/2 or 3x to the first power. So we have our derivative, and we want to set that derivative equal to 0 to find the critical numbers. Now here on the left, we can factor out, it looks like a 3x. So we factor out a 3x, and we're left with this quantity x minus 1 in parentheses, and that is equal to 0. Now we set each factor equal to 0. When 3x equals 0, we have x equals 0. And when this factor, x minus 1 in parentheses, equals 0, we'll have another x value, x equals 1. Now notice too here in this problem, they did not give us a closed interval from a to b. So then we'll just have to assume we're talking about the entire real number line, the entire x-axis, from negative to positive infinity. And here's our x-axis. We're going to start way over to the left at negative infinity, and we're going to go until we run into our first critical number, 0. So our first interval is from negative infinity to our first critical number, 0, and all x values in between. Our next interval is going to go from 0 to 1, our first critical number to our second. So next we're going to have an interval of all the x's between 0 and 1. And then finally, after this critical number, there are no more others, so we're going to head off toward positive infinity. So our last interval is 1 to positive infinity. Now what we're going to do is just take a test value. We're going to pick a number somewhere in each interval, and we're going to plug it into the derivative to see if our derivative is positive or negative, and that'll tell us if we have an increasing or decreasing section of the graph. So for the first one here, let's take a nice easy number. X is -1. Now again, we're plugging this into the derivative function. We want to see if our derivative is positive or negative, or if our slope is positive or negative. That's a -1. So if we plug -1 into our derivative here, we are going to come out with f prime of -1 is +6. +6 is greater than 0, so our conclusion is we have an increasing section of the graph. Between 0 and 1, let's take a test value of 1/2. If we plug 1/2 into the derivative, we are going to get an output of -3/4. -3/4, just the fact that it's a negative number tells us that this is a decreasing section of the graph. And finally, for our last interval from 1 to infinity, let's plug in a +2. Plug a +2 into the derivative, we're going to get 6. Again, just like our first interval here, which is greater than 0. Positive numbers means our function is increasing across that interval. And let's see here, from this information, we can come up with a rough idea what the graph of this would look like. So here's the graph of our original function, x to the third minus 3/2 x squared. First thing we did was found the critical numbers, and those occurred at x is 0 and at x is +1. So those are what chopped our x-axis up into intervals. So we checked the first interval from negative infinity to our first critical number. We tested one point on there and we found it was positive, so we knew the graph was increasing along this stretch. Our next interval went from critical number to critical number, 0 to 1. We plugged in 1/2 and we got a negative derivative, so we knew across this whole interval we were decreasing. And then our last interval went from 1 to positive infinity. We plugged in the test value of 2 and we found that the slope there was positive, so we knew for the entire interval our function was increasing. So example 1 gives you one example of how to find intervals on which a function increases or decreases. The guidelines below summarize the steps followed in that example. So f is a continuous function on some interval from a to b. To find the open intervals on which f is increasing or decreasing, we use the following steps. First, locate those critical numbers. Use these numbers to determine the test interval. Those critical numbers will chop our interval up our interval up into pieces. Determine the sign of the derivative at one test value from each interval. And then we use theorem 3.5 to determine if we are increasing or decreasing on each of those intervals. These guidelines are valid if the interval is a to b is replaced by an interval of from negative infinity to positive infinity, and some critical numbers in between. Now a function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. For instance, the function f of x is x to the third is strictly monotonic on the entire real number line because it increases on the entire real number line, as shown in the first figure down here. F of x is x to the third. If we take the derivative, f prime of x is equal to 3x squared, and we set that equal to 0, we do have a horizontal tangent line at exactly one point, right at the origin. Our tangent line there would be horizontal. And if we look at the function itself, we are increasing. We have positive slope tangent lines as we're coming up. And those tangent lines get more and more horizontal the closer we get to the origin. As we actually achieve the origin, we will have one individual tangent line that is horizontal, and then as we move to the positive x-axis, we start increasing again. So our function increases until we hit the origin. There is one horizontal tangent line, and then we begin increasing again. So it is a strictly monotonic function. The function shown in 317b is not strictly monotonic on the entire real number line because it does have a constant interval from 0 to 1. Here's a piecewise function. If our x values are less than 0 or negative, we use negative x squared. If they are greater than 1, we use this quantity x minus 1 squared. And for the x values between 0 and 1, we just have a value of 0. So we are increasing up until the origin, and then we have a flat stretch, a constant function from 0 to 1, and then we do begin increasing again. This is not monotonic because of this flat stretch between 0 and 1, as defined by the piecewise function. Now this leads into Theorem 3.6, the first derivative test. Let C be some critical number of a function, f that is continuous on an open interval I containing that point C. If f is differentiable on the interval, except possibly at that point C, then f of C, its output, can be classified as follows. If our derivative, if f prime, changes from negative to positive at this number, then we have a minimum value. And this is easy to see graphically. It says our derivative changes from negative to positive. So here's our critical number. On the left side of it, our derivative is negative. We're going downhill. And then on the other side of the critical number, our derivative turns to positive, so it's increasing. If we had negative derivatives and then positive derivatives, right in between there at our critical number, we do have our value C with the horizontal tangent line. If we're going down and then we're going up, that means point C is a minimum. Number 2, if the derivative changes from positive to negative, we have a relative max. So here on the left of our critical number, our derivatives are positive. On the right-hand side, they change to negative. We're going uphill, and then we hit our critical number, and then we're going downhill. That means this critical number has to be a relative max. And we will run into some functions where we will have neither a min or a max. We might have a function, our critical number is right here, C, where we have a horizontal tangent line. To the left, we have a positive slope derivative. On the right, we continue with another positive slope derivative. This point C, it went from positive to positive on the left and right side. It's neither a min nor a max. And the same scenario if it is negative derivatives, negative slopes on either side of that critical number C. Here in example 2, we're going to apply this first derivative test. The directions say find the relative extrema of this function. F of x is a half x minus sine x across an interval from 0 to 2 pi. So the first thing we're going to do is take our derivative and set that equal to 0. So we have our function f of x is 1/2 x minus sine x. To find the derivative f prime, let's see, the derivative of a half x is just a half. The derivative of sine is cosine. So we have 1/2 minus the cos of x, and now we set that derivative equal to 0. I will add cosine to both sides, and we're going to have 1/2 equals the cos of x, or cos of x equals 1/2. I like my trig functions on the left. Now, if we think back to the unit circle, where do we have a cosine value of 1/2? Well, that occurs at x equals 1/3 pi and 5/3 pi. So there's our two critical numbers. And we have, this is not, we're not going from positive to negative infinity. We're just going from 0 to 2 pi. So we were going to chop this interval up into actually 3 smaller pieces. So let's see, our first interval is going to go from the left end point 0 to the first critical number 1/3 pi. And all x's in between. Our next interval would go between the critical numbers from 1/3 pi to 5/3 pi. So 1/3 pi to 5/3 pi is our second interval. And then finally, we're going to go from our second critical number to the right endpoint, from 5/3 pi to 2 pi. So 5/3 pi to 2 pi is our last piece of the interval there. Now we're going to pick a test value for each of these and see if we're increasing and decreasing. And then we're going to think back to here the first derivative test and figure out if these critical numbers are maxes or mins. So let's see here for our first critical number, or our first test value in this interval, I'm going to pick x as a 1/4 pi. Now remember, we're plugging these test values into the derivative. 1/2 minus the cos of x to see if our derivative is positive or negative. When we plug a 1/4 pi in there, we are going to get a negative number. So here our derivative f prime of x is less than 0. So that tells us on this chunk the function is decreasing. Between the critical numbers, a good test value in there is just pi. So you plug pi into the derivative, you get the output of that is greater than 0. Greater than 0 or positive. So we know here our function is increasing. And for the last piece, let's pick a test value of 7/4 pi. We plug that into the derivative here for this x, compute the output, and we get a negative number. Negative output means our function is decreasing. So let's look here at the table, in between our intervals here, right here at 1/3 pi. That was one of our critical numbers. Our function is going from decreasing to increasing. Yeah, on the left of that critical number, it's decreasing, and then we hit the critical number, then we're increasing. So we know that pi over 3 is going to be a minimum value, the bottom of a valley. So pi over 3 is a min. And the other critical number right here at 5/3 pi, our function on the left was increasing. We hit the critical number and then we are decreasing. So we know that this critical number, 5/3 pi, is a max. So our 5/3 pi number was a relative max. And let's pull out our graph here. And here's the graph of our function, a 1/2 x minus sine x from 0 to 2 pi. Again, the first thing we did was derive it, set the derivative equal to 0, and we found a couple critical numbers right here. This would be 1/3 pi, and then right here at 5/3 pi. So we found our derivative, set the derivative equal to 0 to get those critical numbers, and then we tested our intervals. On our first interval from 0 to that 1/3 pi, we were decreasing. And then on the second interval from 1/3 pi to 5/3 pi, we were increasing. So decreasing to increasing, we knew that first critical number was a min. And then we checked our last piece here from 5/3 pi to 2 pi, and once again we were decreasing. So we went from increasing to decreasing. We knew that was the top of a hill, or a relative max. And that's where we'll end this first video here. I'll finish the section, the last two examples, in the next video.